Yeah, I don't think you add this topological barrier phase term can lead to a symmetry breaking phase. Okay, so this is the conclusion. But because so how many minutes?
25.
Okay. Yeah. So because we know that the classification of 3D botanic power insulate actually is Z2Q. So there are 3 non-trivial root phase. So here we only find 1, but actually we don't know there are more in this kind of setup or not. Maybe or maybe not. But at this point we don't have a complete classification because this lambda is in principle need to consider arbitrary kind of lambda. So it's very hard to make a conclusion whether there's something else more than this S08 Cartan matrix or not. But we conjecture maybe there's no other Cartan matrix we can find. All the Cartan matrices we find must be in blocks of this lambda S08. Because this is kind of consistent with the covalence theory and the Sentius theory of this Z2 index beyond the group cohomology. They only find 1 Z2, there's no more. So the other 2 Z2 root phase, actually they are within group cohomology. So for those cases within group cohomology, we believe that this BF theory actually is already sufficient to describe such kind of BTI phase. So the key is that for this BTI phase beyond the group cohomology, we need to introduce additional like a string linking process. But here, it's pretty similar as this 2+1D case, because in 2+1D case, this BTI phase always within group cohomology. So we actually don't change this topological term. We just add some non-trivial symmetry action. For example, on the vortex field, you attach a spin and it has a non-trivial transformation on the time reversal. So here, the principle is pretty similar, that if we just starting from some trivial BF theory with this diagonal K matrix, and then we can introduce some non-trivial definition of symmetry transformation for this B and A field. There may already derive some non-trivial BTI phase. So then we consider in such kind of possibility, and in the end we do find this Z2 root phase, 2 Z2 root phase. So the first one, it's relatively easy. You just think about kind of in general, this U1 symmetry can be defined in some abnormal way. So in a normal way, this external gauge field is just coupled to the two-form gauge field. But abnormal in the sense that it's like this Vortex-line also carry charge. So this Z2 gauge field can also, so this external gauge field, F mu can also couple to this A mu gauge field. So if we turn on such kind of general 3D coupling, and actually we can integrate this internal BF dynamic field and end up with some electric magnetic response. It's pretty like a topological insulate. And in a boson system, you can show that this coefficient is always 2 pi mod 4 pi. So now we find this 1 Z2 index. So the other Z2 index is relatively hidden and not so straightforward. The reason is that the other Z2 index actually it's nothing to do with this U1 symmetry. Even you break the U1 symmetry, it's still stable. So it cannot be detected by any kind of electric magnetic response. So actually this case is pretty similar like the previous this beyond group cohomology case, because there I have never emphasized this action of U1 gauge field, which actually formally, if you start from this BF term plus BYGB, you don't need a U1 gauge field, it still work because there's no global symmetry. There are only gauge symmetry, but a gauge symmetry is not a symmetry, just a redundancy. So the theory actually only rely on this time reversal symmetry action. So U1 symmetry action you can assign anyway, it's still stable. But only in this case, this U1 is crucial. And when you U1 symmetry, it's non-trivial. You can define this electrical magnetic response. So this case, it's the case that we also don't need this U1 symmetry. It's enough to just consider this non-trivial time reversal action. So so the point is that we can define some exotic time rotor symmetry action for the one form and two form gauge field. So typically we know that this one form gauge field just transform in this standard way, and two form gauge field also transform in this standard way. And if it's time rotor symmetry, we require this matrix TA and TB twice must go back, must be 1. And but this TA and TB, we can also redefine them up to some GLNZ transformation, because we can redefine this B and A term up to some GLNZ transformation. So that's why we can have this equivalent class here. So the reason we can have two different ones, because this one form gauge field and two form gauge field, they can be defined as separate GLNZ transformation. However, we see that regardless what kind of GLNZ transformation you design, once you determine this matrix TA and TB, the determinant of this T will not change. That means that in the end, we can have two possible patterns. The trivial pattern, which is the normal definition of this kind of TA and TB, which basically just a diagonal. So it turns out that the one form gauge field transform the determinant is just 1. A two form is a kind of minus 1 for each component. So if you have n component, just the power n. But there could be a non-trivial one that both of them have an additional minus sign. So this is corresponding to minus 1. So in the end, I will tell you how this is connected to this so-called ETMT SPT phase, BTI phase. But before doing that, I want to discuss slightly more about this U1, this BTI phase with some twisted U1 action with a non-trivial electric magnetic effect. Because in Santos' early argument, he showed that this kind of state, the surface topology order corresponding to this so-called ECMC. ECMC means there could be a surface Topological topology order. I think Jay mentioned this Topological for many times today and yesterday, so all of you may be familiar about that. So the Topological basically can have 4 quasi-particles. So there's the identity particle, and E, and M, and the bounded state F. So the Santos' argument is that the ECMC is that both E and M carry some 1/2 U1 charge, such that you can never realize such kind of Topological with the U1 symmetry in purely 2 plus 1D. This is quite easy to imagine because if both E and M carry U1 half charge, basically the U1 conservation becomes something like E plus or E minus M. That means you can turn to the conservation kind of tie this E and M, but for a charge, this M is not a local object. So if we put these two things together to design a conservation rule in 2 plus 1D, it's impossible. And that's why it's so-called obstruction, or it's corresponding to anomalous surface theory, which identified this one of the root phase of BTI. So here I will show you a recipe that we can naturally derive such kind of ECMC kind of states from our previous setup. We can just assume that we're starting from some general kind of 2x2 BF theory, because in general we can put this to be arbitrary kind of n by n. But in order to just find this some simple topology order, actually 2x2 is enough. Okay, then we can just design the coupling in such a way. Means that both Q1, Qi, and Q prime I, this kind of couple to the 2 form, the charge for the 2 form, this is charge for the 1 form. We only choose this lower component non-zero, so just like a convention or some charge vector. Once you choose in this way, this coupling term just you can write down in such a way. So they only now manage for this second component of the A and B gauge fields. And also we note that this charge, because it's a Z2 charge, so they can be identified by this +2 shift. Okay, so now let's do some formal calculation just by integral out this A1 gauge field in the 2 component BF theory. Then this B2 basically becomes some total derivative. So you just put this in, And then you can see that there's a topological term. So this term actually is topological term describes this Z2 Tori-code topological order. Basically, it's like a K matrix 0 to 2 0. So it has the ground state degeneracy 4. And in addition to this kind of term, there's a couple of coupling term, like this one and this one. And and in the end, we can just simply integrate all this internal gauge field, and we can look at this magneto-electric response, and we find that the coefficient is just Q1, Q2. And if we choose both Q1, Q2 to be 1, then it's a non-trivial response. And on the boundary, you will also see that on the boundary, naturally, you can have some coupling to this external gauge field, which allow us to determine this U1 charge for this E and M particle. And it turns out both of them are 1/2 from this kind of standard coupling boundary. Yeah, so we just choose both of them to be 1. Because there's no choice. Q1, Q2 can only be either choose to be 0 or 1. So there are 4 possibilities. You can choose Q1 equal to 0, Q2 equal to 0, Q1 equal to 0, Q2 equal to 2, okay, equal to 1. So only for this, both one possibility is non-trivial. All the other cases, they are trivial because this electromagnetic response vanish. Okay, so here we find that we have a systematic way to reproduce Sandhill's previous result for this ECMC state. But moreover, because we construct this bulk theory, we should be able to consider more general topological order. So here we give just one simple example that we realize this ZP topological order, not just Z2 on the surface. But we can just do the similar thing and choose a similar charge vector. And in the end, on the surface, you will find that this kind of fractionalized charge can take this following value. Here we need some additional parameter L1, L2 because for ZP gauge field there are more quasi-particles. And these L1, L2 are parameterized, are kind of parameter that labeling those additional quasi-particles. So there are basically many, basically there could be P square minus 1 quasi-particle. So in the Z2 case, only 3. So this is E, this is E, F, E. This is half charge, half charge. This is F is integer charge because it's a bound state. Okay. But here we also have some restriction because in the coupling we have such kind of periodicity, and it turns out P must be even. It's just like we can only take Z2, Z4, and Z6. If we take odd, this coupling is not allowed. It will break time reversal symmetry. So we only consider this even case. And if we consider even, the conclusion is that we can have this surface Hall conductance in this following expression. And then we can discuss several cases. For example, if like this Q1 is 1/2 of P, and Q2 is odd, and then it's a BTI phase. And all the other cases, they correspond to trivial or symmetry breaking phase. So in this choice, it's a non-trivial BTI. So let me just give you some example. For example, if we choose Z4 gauge field, P equal to 4, and Q1 equal to 1/2 is 2, and Q2 equal to 1 is odd. Then the charge vector for this Z2 gauge field, it's like a charge for each particle of this Z4 gauge field just can be expressed in this value. And if you take L2 equal to 0 and L1 equal to 1, then you can find that this minimal charge in the Z4 gauge theory actually is quarter charge. It's not half charge. So only for Z2 gauge field, it's half charge. But here, in general, Zn gauge field, we can have more fractionalized charge. So from this kind of point of view, we also understand that this surface anomaly typically is not one-to-one correspondence to the non-trivial property of the bulk BTI. In principle, for each given bulk BTI, you can have infinite number of different surface topological order. Okay. And for this time reversal symmetry, in principle, we can also construct a different topological order. But here I just want to show that the one corresponding to this ETMT. So for the ETMT, we can just choose this the similar K matrix as we do for this ECMC. And on time reversal symmetry, we will see that it transforms to K prime. So there's some minus sign here, but we can then apply GL to the transformation to transform it back. But this TA and TB will be defined in such a way such that determinant is -1. This is also -1. So in this case, it's a non-trivial transformation. So again, we can integrate out A1, and we end up with some toric code-like action. And for this toric code action, it's time reversal symmetry transformation actually is strange because in the usual time reversal symmetry transformation, this A tilde and A, they should transform in a opposite way such that this term is invariant. So in such kind of transformation, you can show that this electric density and flux density, they both of them change sign. So this is actually consistent with the fact that both E and M particle carry some spin. Because only when they carry spin, this density like spin density, they will change sign on time reversal. So here we cannot explicitly produce this ETMT, but the feature we find in such kind of theory is consistent with the ETMT theory. But in our setup, we not emphasize on the precise surface anomalous topological order. We just try to understand how many inequivalent cars we can have in the bulk. So the conclusion is that we can have a Z2 cars by define this time reversal in some exotic way. So now we, in the end, we have all of the Z2 cube different phases. Okay, so I almost finished. I think finally, just I try to mention that such kind of construction can be generalized to many different symmetry. For example, we can consider this Zn symmetry. So for U1, we know it's not quantized. But for Zn, actually, we can argue this lambda actually can be take n different quantized value. So we can just do the argument the following way. We can assume we turn on some external background two-form gauge field. And this external background two-form gauge field, because it's Zn, so we can here must have coefficient n. And once we turn on such kind of coupling, this external two-form gauge field coupled to this internal current, then we can integrate this internal gauge field and make a response. And this response theory, it's easy to show that this lambda must be take some quantized value. Actually, lambda quantized at 1/n, and also lambda have a shift, which is equivalent. Two states become equivalent if we shift lambda to lambda plus n squared. In the end, you can show that this is only two constraint, like lambda over n must be integer, and lambda plus n squared must be identified. So for example, if we consider n equal 2 for Z2 gauge field, lambda and lambda plus 4, they are the same. But lambda minus 2 must be integer, so that means lambda can only choose as 2 as a non-trivial phase. We can only choose like 0, 2, 4, but 4 already equals 0. So the conclusion is that for that case, we have a Z2 classification. But for Zn, it's very similar. You can have n possible cases. But such kind of theory, the global symmetry, is slightly different from the usual global symmetry. We think about the global symmetry acting on the particle. It's a global symmetry acting on the string. So recently, people doing string theory actually they are interested in such kind of so-called one-form global symmetry. So basically, it's a symmetry acting on the string, acting on this extensive objects. Then we can find some more non-trivial SPT phases that are beyond the group cohomology. So for the global symmetry action on the particle, I think there might be no additional phases if we only consider unitary symmetry. But I'm not sure, Xiaogang, so in your theory, in your recent theory, is this true for any unitary group? There's nothing beyond the group of cohomology.
And in 3+1.
Yeah, 3+1. Yeah, so.
So I wonder, actually, that's my question. So here, do you have for the Zn symmetry? Do you have a new one? I mean.
Yeah, have a new one.
Cohomology, there's a Zn, right?
Yeah, but the key is that it's not a usual symmetry on the point-like particle. It's a so-called one-form symmetry. So it's a symmetry that the symmetry charge carried by a string, not carried by a particle. But as a global symmetry, such kind of exotic symmetry is allowed actually. Then we can turn on this two-form gauge field as a detection to detect this non-trivial.
So the bottom line is that there is additional. So what is the classification? You know, group cohomology to Zn. So using this, you get another Zn.
Group cohomology is nothing. It's trivial. H up 4 Zn U1 is trivial.
So 3+1.
Yeah.
Oh yeah, it's trivial.
Yeah.
But, so here you get another Zn.
Yeah. Here have a Zn classification.
But the classify what?
Classify this SPT phase associated with one-form symmetry actually.
But what is one-form symmetry for the Hamiltonian? I mean.
Yeah, that part I'm not quite clear. Yeah, I think in a simple picture, it's like some system formed by a string, and this string carry charge. So, in this sense, I'm not sure it's a restricted local Hamiltonian or not.
I see.
Yeah, it might be not a local Hamiltonian.
So usually when you have a string which carry charge, that
yeah.
means it's topological order.
Yeah, but the point is that when string carry charge, it can still have non-trivial confinement phase. It's like a confinement phase here.
I don't know.
Yeah, even string carry charge sometimes can confine and it can get some strange things.
Is this charge global charge or gauge charge?
It's global charge.
If it's global charge, that means you have a Zn symmetry then.
Zn global symmetry, yes.
And
it's kind of a confinement phase with a Zn global symmetry. Yeah.
But you say this Zn is not a Euro symmetry, but some kind of some higher symmetry.
Yeah, some one-form symmetry. Yeah.
But the one-form symmetry, then it's not global symmetry. The global symmetry, the global symmetry have a Euro definition. So if your symmetry don't have a Euro definition, then maybe it's called different.
Euro symmetry, I think it's if we define the symmetry action on a particle, it's one way. But
the Euro symmetry is not defined on the particle. Euro symmetry is defined on the Hilbert space. So you have a many-body Hamiltonian with a many-body Hilbert space defined on the Hilbert space. So there's no, that's before the particle. I think there's an issue about what is this higher symmetry, and there's possibility that the higher symmetry is not symmetry to gauge. So actually, the higher symmetry corresponds to this topological order. Actually, if it's not, then it's not SPT. Yeah, there's some issue here.
I think last week Davide have a paper and he also talked about this.
That's what I mean. I'm not sure what they're talking about is a symmetry. They
I
talk
see.
about topological order.
I see. Yeah, okay, we can discuss this later. So here just a kind of a formal calculation from this df plus dydb term looks like that there's chance for more SPT phases beyond this group of cohomology class. Okay, yeah, I finished. Okay, so the main point of this talk is that by introducing this BYB term, in addition to the BF theory, we can explain this microscopic origin of this BTI phase beyond the group cohomology class. And with purely BF theory only, but with non-trivial symmetry twist, we also explain the origin of this C2 square SPT phases within group cohomology class. And from such kind of view, it's very optimistic for searching for this realistic Hamiltonian, because we understand this kind of physics actually is very simple. So like here, we just want to some vortex-line have some non-trivial linking. And for this case, we want to this kind of vortex-line carry charge or carry spin. It's pretty similar as the 2+1 case. So for this ECMC, it's almost like vortex-line carry charge. But for ETMT, it's like vortex-line carry spin. And in 2+1, we know if the vortex carries spin, we can end up with a non-trivial BTI phase. So it's like just a symmetry declaration for this usual VF theory. Okay, so but the most interesting thing, I think, if we apply such kind of concept for fermatic SPD phase, maybe there could even more SPD phases that beyond the group super cohomology classification. So, which means that we, in the presence of strong impressions, there could be chance find more fermatic Tauber insulator that beyond this free Fermat theory. Okay, thanks for your attention.
Questions or comments? Yes.
Yeah, for your last reading example, can you compute the ground state generously?
In the last example.
Yeah, this is the example.
Yes, in this example, the ground state degeneracy only rely on the coefficient here. So in the response theory, it's N2Q, but in the original theory.
But both A and B are dynamical here.
Right.
So it's not very obvious why the ground state is only do not depend on lambda. I mean, it's a quadratic theory. If you really quantize that, that's really don't depend on lambda.
I think so, because without symmetry protection, you can remove this term.
No, that's not my question. So in the presence of lambda, that's theory. With the lambda, what is the ground degeneracy? So it's just this particular theory, whether ground degeneracy can be computed or defined. It's not about removing one. Just for this theory. So this theory is given. The Lagrange is given. So what is the ground degeneracy of this given theory?
If we assume A mu is non-compact and B mu is compact, then the answer is 1, because you can simply integrate A mu.
But there's possibility maybe A mu has to be compact. I mean.
Actually, from the original derivation, we find that A mu is non-compact. Yeah. So for compact, I don't know.
Okay. Yeah, non-compact is.
Any more questions? Comments? Or if not, let's thank two speakers in this afternoon session.